All right, welcome for those of you who are stumbling in a little early. We're going to get started in the next minute or so. Let some people who are maybe stretching their legs, grabbing something to drink, let them filter in, and we can all get started. All right, we are at 1 o'clock. I'll wait one more minute before I really get started. So what I'll do now is fill the next minute with just a huge thank you for everyone who joined and registered and is hopping into all of our presentations and being active in the Q&As and everything. We've had some really great questions, some really great dialogue, and I really appreciate that. Keep them coming. So whenever you see the Q&A feature, feel free to drop in a question about that current session. And if you have any questions, as a quick reminder, about anything sort of logistics related for the training, head over to like the main page on the either in the Whova app or on the Whova web page for this event, and you should have some answers there. All right, I think I properly filled that minute and let everyone else who's hopping in hop on in. All right, so welcome everybody to our first live modeling session. We're going to see some fun things happen here. I hope everyone had the opportunity to listen to all of the videos that myself and Hassan and Lindsay put together, sort of describing this training and some of the cool things that we're going to be talking about. Hope you're able to dive into all of those, because this is definitely going to build off of the video that you hopefully just watched, that I was talking about for intermediate modeling concepts. So for us to sort of actually get hands-on with some of this stuff, again, we're going to be working through Google Colab. So these notebooks are available in the description for this session. So just scroll on down and click on that. They're also available on our GitHub. If you go to Gurobi's GitHub, modeling examples, optimization 201, you'll see a folder for modeling session 1, and you'll get to this as well. If you do ever get lost or anything like that, we have a completed version that looks exactly the same, except for my runtime was disconnected. That looks exactly the same, but it has anything that is sort of question marks and saying, something that I'm going to give you guys a few minutes to fill in. That stuff's already filled in, so you're able to catch up if you get behind or anything like that. So let's dive into the problem that we're going to use for this example, and it is the same problem, at least from a starting point, that we had for Opti201, which was essentially it was a small toy problem where we have a company that produces and distributes widgets, and essentially we have several production facilities and several other distribution locations that would then sort of sell our widgets to local vendors and sort of go on from there. If you want to take a look at that example, maybe there's something you want to have it sort of side by side, be able to flip back and forth. I did put a link to it at the top of this notebook. And it'll look something like this, translating a decision problem to an optimization model. A lot of this goes through the basics of optimization, talking about decision variables, constraints, and parameters, and objectives, and everything like that. So we're assuming we remember all of that because it's all right here. I do want to sort of review some of the aspects of the problem that are important for this part, where we're going to expand upon this model and apply some of the things that we were talking about in the last session. So again, we have our production facilities, which we labeled with set P, and I found some of my favorite cities. I'm a Cleveland native. Anyone else from Cleveland? Going once, going twice. Okay. So that's our set of production facilities. We have a set of distribution hubs or locations or other facilities. I think I use all of those words to describe the distribution locations. And we have that set defined here. So this, then moving on to our model parameters. So these are a couple of the important numbers that we are going to have for this problem. We have the transportation costs. So what does it cost to ship a particular widget from one production facility to a distribution center? And then we have a couple other things like the maximum production that a facility can have and the demand at a certain hub. So these are all, again, some of the same stuff that we had from the earlier version of the Opti201 problem here. So let's dive in to actually running some cells and having fun here. So we always have to start with a quick pip install of gurobipy. This is a great way to just get a little taste of the functionality, or a full taste of the functionality, but a little taste of the solving power. And whenever you install a license like this, it's limited to just 2,000 variables and 2,000 constraints. If you get fancy with quadratics, it sort of lowers from there. So let's install that. I hope everyone trusts me by now that you're able to click run anyways. And we're going to install gurobipy and then import pandas and then import our awesome gurobipy package. So what we have now is things like the data that I was just describing about the costs and the production. So we're defining all of those sets, defining all of that, those numerical values that we need. And one thing that is part of this problem that you may forget is we have an upper bound on the amount that a facility can produce, but we're also setting a lower bound as well as 75% of that max. So that's something that you can play with if you want to moving forward and as you sort of keep using this example. So I'm going to, in the first time we went through this problem in Opti201, went sort of through a lot of this stuff step by step. Here are our decision variables. Here's our constraint. This is what all this, blah, blah. So again, sort of assuming that this is some common knowledge and we're able to sort of get past this a little bit more quickly. But I do want to quickly review what our decision variables are and our constraints at a quick high level. So again, our decisions that we have in this model are it's the amount of widgets that are produced at facility P and shipped to distribution center D, and we're denoting that by XPD. And we have a few constraints, min and max production, and also that the demand at those hubs are met. And our objective is to meet the demand at minimal cost. So here is the formulation. And in the last session, I sort of stressed the importance of of not skipping this step and going from what people are describing to you in words, going straight to the code, because again, this is the common link between the two. And also other people who are modeling, who are optimization modelers will definitely be able to understand what you're writing here. And it's just a good way to communicate the problem. So here's our objective and all of the constraints and the definition of our decision variables. So this is the chunk of code that mimics the formulation that we have above. So we run that. And again, a couple of things. One thing that I want to mention about some of the syntax that you may see and some of the ways that I did things like summations and stuff. Thinking back to Opti201, again, that was a very introductory session. So I wanted to keep things very consistent. And so using things like quick sum I may have used it when it wasn't completely necessary, but I used it in order to keep things consistent. You may, and I also didn't really use a lot of Gurobi sort of native data structures like tuples, tuple dictionaries, and things of that nature that you may be familiar with if you're a little bit more hands-on with Gurobi. And that's because, again, I wanted to keep things consistent. So you may be thinking, oh, it'd be much better if you wrote things this way or use this. That's probably true. And maybe in further sessions, I'll start further trainings, I'll start talking about that a little bit more. But for now, we're just sort of keeping things simple. So keep that in mind as you go through this. So we established all of our constraints. We established our decision variables. We set our objective. We can click go and optimize. And did a couple things different is from the 101 example. We're storing the objective. And that's what this line is doing right here. So we're taking our model and just gathering the objective and then getting the value by calling the objective that we just stored and using this get value. This is a great way to, if you need to sort of get quick access to a set of variables, some linear expression of variables. This is a great way to sort of set that up and then use this get value to quickly get those values. So as our optimization log, our Gurobi log, and we see that this is essentially everything that was from 101. We have our minimal cost. And this is our production sort of schedule. So we're shipping things from Baltimore to Nashville, 19 units of widgets, Baltimore to Richmond, 116 widgets, so on and so forth. So this is where we more or less left off in Opti201. So everything from here on out is new and improved, and hopefully a nice expansion to a simple problem and let you understand sort of the awesomeness of mathematical optimization, sort of getting a little bit more of sort of an idea of what the true sort of power of optimization really is. And then also how our team at Gurobi, how we approach easing the modeling, making the modeling process easier for everyone, whether you're an expert or new. That's something, we definitely take that to heart to try and make things easier for everyone. So in the last session, I specifically called out a table that looked exactly like this. And I was thinking, hey, maybe one of these values, maybe even two of them, but one of these looks kind of weird. It looks like it may not actually be something that you'd want to do if you were actually, in charge of this production and distribution sort of problem. And that is this little 2 here that says that we want to ship 2 units from Cleveland to Nashville. And that may not be actually tractable. That may not be something that's actually possible for this problem. If you're thinking about sort of large scale distribution, shipping 2 units of widgets, depending on what our widget is, that's just throwing something in an envelope and putting it in the mail. Is that something that we can actually do, particularly at this cost? So we're going to fix that. And in the last session, I sort of went through what is a bad way to try and fix that. And a bad way to try and fix that would be to say, okay, I want to add a constraint. XPD must be greater than or equal to some lower bound on what I decide to send C. Maybe it's 10, maybe it's 30. And I explained why that's not a great idea, because what that would essentially do is that would enforce every distribution center to every production facility to every distribution center to send at least that much. So what we saw was there was a flaw in that logic. So essentially what we concluded for that problem was not that we needed that specific constraint, but we needed something similar. We needed an if-then statement. So we needed to say, if widgets are shipped from a production facility P to a distribution center D, then it must be at least C units. So it's saying you must be C or nothing at all. That's kind of what this is getting at. So in my first little, and one thing that I want to mention is it may be, especially right now, if you have like a some paper, pencil, or something like that, something to jot down on. I'd suggest getting that out at this point, because the first couple things I want to ask you and give you a minute to sort of think through, they're not actually typing any code. It's more of the formulation side of things. So so that's what's it's easier to sort of write that stuff out pretty quickly. So we have this statement that we sort of agreed that is the right way to go about solving this problem of the small shipment value. And again, if widgets are shipped from P to D, then it must be at least C units. Let's replace some of those words, widgets shipped from P to D, and then it must be at least C units. Let's replace that with our decision variables. So again, when we say widgets are shipped from P to D, what does that mean in terms of our decision variable? And also then then that shipment must be at least C units. What does that mean with relation to our decision variable? Again, our decision variable is XPD, shipping widgets from a production to a distribution center. So this is sort of what I want you guys to sort of fill in right now, is this if then statement. And I'll sort of give a minute for you to think through that, and then I will show the cell that has the answer hidden. So while you're doing that, I'm going to take a sip of water. I'm still going to give you another minute or so, but I'm just going to comment about how hard it is for me to wait an entire minute. About 8 seconds of silence seems like 10 minutes while you're doing this. Okay. So, so if we were to sort of write this statement out, but again, strip away some of the words, add in our decision variables, this is what we would have. If widgets are shipped from P to D, so that means we ship something, it's positive. Then XPD must be greater than, it must be at least C units, so it must be greater than or equal to C. One note, I guess, from here is if you sort of did something like XPD must be greater than or equal to 1, that's, sort of, you're assuming some integrality of widgets that you can't send half, which is quite reasonable for this problem. So I would give you credit for that too, if I was back into my teacher time. But given sort of how we've been talking about X as a continuous variable, even though it is quite possible that you can't have a third of a widget, we're going to say X is positive, and then X must be at least C, greater than or equal to C. So far so good. We've reduced some of the words into some notation, and then so let's rewrite this statement using that if then to or equivalence that I mentioned in the in the previous session. And if you're familiar with that, if it's up here, great. Then it's great that you internalize that. But essentially, if you need a quick reminder, it's I guess I could say it very generically. If then moving to an or statement. So if you have if A then B, you can rewrite that as not A or B. So then think about what A is for this, what B is for this, and sort of again jot this down real fast. I'll give you another minute for that. So remember, if A then B is equivalent to not A or B. And as another 30 seconds of filler, if anyone here is still at college or anything like that, and you have an opportunity to take like a symbolic logic class, that was one of my favorites. Highly recommended. Highly recommended. Along with at least an intro stats. That's my two requirements, I think, for anyone in college. Okay, wasted enough time. So ignore the question marks for now. That was just my reminder to make this a question. So then if we wanted to translate this over to an or statement, then we negate that first part. So the opposite, not positive of, if a value is not strictly greater than 0, that means it's less than or equal to 0. And then we just keep the second clause there, the then clause, and keep that exactly the same. So it's XPD is less than or equal to 0, or XPD is greater than or equal to C. So let's again let's sort of write that down. We already know that XPD is non-negative. So that means it must be greater than or equal to 0. So if something is, we already know that, and again, let me backtrack for a second. One of the sort of general assumptions about all decision variables in mathematical optimization, unless otherwise specified, you just assume that XPD is non-negative. And I think we talked about that in the formulation, but I just sort of want to highlight that as something that if you don't see it, it's sort of just there, unless otherwise specified. But again, great note, a nice formulation will have that there, just so everyone's crystal clear. So if XPD is non-negative, and then it's also less than or equal to 0. So if it's greater than or equal to 0, less than or equal to 0, pardon me, lost my train of thought, then it must be equal to 0. So that's one way that we can sort of strengthen what we have above. So now, how do we actually model this? So we have this or statement. What do we do next? We have a few approaches. One is what we call a big M constraint, and this is something that I mentioned again in the video that we just from the previous session. We also have what we call indicator constraints, which are a super easy way to implement big M, but without having to worry about a lot of the work. And then we're also going to talk about a different variable type that you can use in Gurobi as well. And all of these 3 different ways are going to do the exact same thing. But we're going to go through them each just so we can sort of, again, compare and contrast, and working through some of this logic using big M, even though it may not be the most efficient way, it's a great way to learn, again, how to do some of the modeling, and then get you sort of some steps to be able to do more complicated models. So before I move on, I made a particular note. You won't see this in your notebook, but I wanted to make a note about it so I didn't forget about why big M constraints can give some issues. So I'm going to give a little bit of an answer, and then we have on with us one of our experts, Eli. So if you feel you want to hop in after I talk for a minute, just you're more than welcome to. But what's great about big M constraints is that it does allow you a lot of flexibility. You have a lot of control over how you can model certain things, and you can really get into some complicated interactions and relationships, and it is a very powerful tool. It's sort of, that's why it was implemented, that's why it was developed, and that's why people use it, and why optimization folks still talk about it. But it can give you some issues. Part of what big M is all about is, and you may see this more in sort of papers and things like that. And that I'm going to set m to be 10 to the 6th or something like that, some huge number, just to make sure that I'll never have to worry about it, the m being an issue. As we sort of talked about, you need to make sure that you choose a decently large m, so it doesn't give you any extra constraints or any extra restrictions. Well, if you have m's that are in the millions or billions or something like that, and then you also have other coefficients that are decimal places or tenths, hundredths, or something like that. Having that wide sort of distribution of numbers in your model can lead to some numerical instability. And again, when you're thinking about how these things are solving, there are sort of just basic operations happening on the back end of addition, subtraction, multiplication, all that sort of stuff. And then there's, again, truncation and rounding and things like that. So you can end up with some problems from that if you choose big M, if you choose your M's sort of poorly. So that's why you always want to try and choose the best M's if you need to. But what I would suggest, particularly at this level of optimization, sort of in this intermediate level, what I would suggest is, if there exists other options that do the same thing as big M, so we're going to talk about indicator constraints and different variable types. If those do the job for you, what you want to do, I would highly suggest using those first as opposed to big M. So just so you make sure you don't run into any of those issues. That being said, we are going to go through using big M just because, again, I want for everyone to understand the logic and understand how the modeling process works. So so that's my spiel. I don't know if Eli, if you have anything to add, or if you think I did a good enough job, I will continue.
Yeah, sounds good to me.
Awesome. Okay. So let's model this OR statement using our big M constraints. And again, what our goal here is to make sure that we represent this statement as as accurately as possible, and when certain binary variables that we're going to implement, they turn the right things on at the right time, and they turn things off at the right time, sort of. And when we in that last session, I had factories turning on and distribution centers turning off and all that sort of stuff. We want to make sure that we replicate that. To replicate this OR statement, we have two clauses in the OR statement. So we're going to use two auxiliary variables, Z1 and Z2. Auxiliary variables are sort of the shorthand name for sort of these helper variables that we use to help us model these on-off switches, these yes-nos, these true-falses, and everything. So the inequality on the left of the OR, x is less than or equal to 0. Again, we want to make sure that the general point is to enforce a desired constraint when a binary variable takes a specific value, and then we want to make sure we're hands off. Otherwise, we sort of have no impact on our decision variables otherwise. So it's clause 1 of the OR statement. We can write this using the a simple big M constraint, and this is essentially exactly what we had in the last session, that same inequality. But I'll give you a quick, a few seconds to think about. Okay, I have x less than or equal to 0. I want to have a scenario where if I have a binary variable take a certain value, then this inequality is enforced. If it takes another value, the other value, then we're not implementing any constraints realistically. So take a few seconds to think that through, and I'm going to take another sip of water. Okay. So our first constraint here is just going to be x is less than or equal to some big M1 times Z1. So when Z is 0, 0 times M is 0. So we have our constraint there. If Z is 1, then we have x is less than or equal to M1. So assuming M1 is large enough, we're not putting any restriction on x. So for the right side of the OR statement, we have x must be greater than or equal to c. Again, we want the same thing. One with one value of an auxiliary variable, we want the desired inequality. The other value, we don't. We want no restrictions. So think about what that would look like. This one's a little bit harder, but take a few seconds to think about what that one may look like. We want something that when our binary variable is 1, something happens. When our variable is 0, we want something else to happen. And again, those two things need to be enforcing this constraint of x is greater than or equal to c, and also enforcing no constraint at all. And while we're doing that, I see a question about someone having a black screen. That may be through the Hoover integration of Zoom. So someone will ping you real soon to help with that. So if anyone else is, reach out and we'll help. Okay. So here is the inequality that helps model this sentiment, this statement here. So x plus m2 times z2 must be greater than or equal to c. So if z2 is 0, then z2 times m2 is 0. So x just must be greater than or equal to c. That's our constraint that we want. If z2 is 1, then just as long as m2 is large enough, there's no restriction. We're always going to have a true inequality as long as m2 is greater than or equal to c. So it doesn't matter what x may be. And again, since x is non-negative, we're assuming that, then we're good to go. So now we need to know how the auxiliary variables, the z1 and z2, sort of work together. So since this is an OR statement, we need one of these things to happen, at least one. So what does that additional constraint look like just within Z1, just with Z1 and Z2? So take a minute to sort of think through that. Okay. So since we need at least one of these things to happen, either Z1 or Z2 has to happen, then you say that the sum of those two things must be greater than or equal to 1. Again, Z being binary variables, this ensures that one of them, at least one of them, is sort of turned on. But then we sort of think, can both of these things really happen together? Can Z1 equal Z2 equal 1? Then, if you sort of think about the absolute value example that we talked about in the last session, you sort of have these two disjoint sets. So it's actually not possible. So what we can do is just strengthen this to say Z1 plus Z2 is equal to 1, and then do a little bit of, toss the Z2 on the other side by subtracting, and then we can substitute and have a nice little simple two sets of, two constraints that we need to look into and implement in our model that will help us sort of go through and model this relationship that, again, this is stemming back to making sure that we want x to be either, 0 or something that's greater than or equal to c. So here are our two constraints. So we did this generally with no subscripts, just so we're not continually writing them over and over and over again. So let's take this back to our problem, and we need to sort of think the relationship again between the x and the z. This is for each combination of production facility and distribution location. So we just sort of let's just chunk on those subscripts and rewrite our two constraints like that. Okay. So lastly, before we get to actually implementing this, let's figure out some good choices for M. I'm making a quick note so I don't forget. Okay. So what are some good choices for M that we can think about as an upper bound for XPD? Is there something that we have already defined as an upper bound? And that certainly is the case. So and that is the max production. So while we said that the sum over P, or excuse me, the sum over D of XPD must be, less than or equal to this max production. So we can't send out more than this max production from each facility P. If we use that as an individual M, there's no way that you can send to one location more than what you can send to all locations. So this is a decent choice for M. Anything lower than that would be too restrictive, because it certainly could be part of your optimal solution, depending on numbers that you may have in future scenarios or something like that, where you have one production facility make everything that it can and send it all to one location. So if you use anything less than this value, then you may be restricting your actual true optimal solution. And for M2, the clear choice is C, because we sort of talked about that, that relationship as well. So let's actually start coding this up a little bit. First thing that we're going to do is add our auxiliary variable Z, again, indexed by P and D. And then first chunk of code that you can mess with is, all right, so we have our Z. How do we code up that first constraint? Again, going back to this up here. How do we actually code this up into gurobipy? So take a minute to take a stab at that, and then I will paste the answer in there just to make sure I don't make any typos, because I am really, really good at typos. And then we'll sort of go on from there. So take a minute to figure that out. All right. I think I might just plop this in here for us, and we can see the answer. Make sure I didn't skip any cells, because it's been a while since we've had a cell to run. Okay, last one, I think I did. Okay, we're all good. Just want to make sure. If I get an error here, then I apologize. But okay, so I'm going to replace these question marks with our good old answer of, it's the exact same thing. XPD must be less than or equal to the max prod P. That's our choice for M. And times 1 minus Z. And then the second one that relates to C, how do we code that up? Pretty similarly. I'll give you a few seconds to try and type that up. Let me run this. Hopefully everything's good. All right, everything's good. And oh yeah, we have yet to actually solidify a value for C. I've been saying this value C, the value C. That's up to the individual instance of the problem. So we're going to set it at 30 for now. Let's delete the question marks and add in the code. Ready? 3, 2, 1. All right. So here's how you code up that that other constraint as well. Again, replacing C for M2. And you may be thinking, whoa, we can do more to this. There's a little bit more algebra fun to be had. That's certainly true. And get ready for the modeling, for the exercises to come after this, if you really want to do some algebra. So let's run that. Let's look at the solution. So we, again, I'm storing this solution so we can sort of look at the values and everything. And voila, we see that 2 is gone. There's no more Cleveland to Nashville at all, which makes sense. If it was only shipping 2 units, then saying that we can't ship anything less than 30 makes it, it makes sense that we just sort of get rid of that sort of arc altogether. And we see that Baltimore to Nashville, which was 19 in the previous, so that did violate this, although it wasn't as bad, that is at the minimum of 30. So we fixed the problem. Hey, congrats to us. So the next question would be, okay, well, how does that change our objective value? Did this blow up the amount of the cost that we have? Are we bankrupt now because we implemented this? For this particular example, with all these particular numbers, the answer is no, although it certainly could for other instances. So the updated model only has an additional cost of $43. And that's a small relative change from, we're dealing with the updated cost is 1748, so 1748. That's only 43 more than the original, so that's not too bad. So that was a lot. That took a long time. Remember, this was just that one constraint, the one idea of, hey, we had 2, we need to fix this. But we went through all of the logic. We understood the if-then statements. We converted to ORs. We take those ORs and thought through them. What happens if Z is 1? What happens if Z is 0? After introducing these auxiliary variables, we went through a lot. But again, all of that stuff is stuff that you need to do for other examples, for other modeling things that you need to come across. But you may be thinking, okay, in the previous session, you talked about how, modeling OR statements and just sort of modeling these alternative constraints can be very formulaic. Is there a better way? And the answer is yes. And this is where indicator constraints that you can use within Gurobi are very, very useful. And this is something that, I wasn't super privy to early in, when I was in consulting and stuff like that. And I would always model, when I was doing optimization, I would always model things with big M just because that's what I was taught. But now, and this is part of what Gurobi tries to do as a whole, is try to simplify this. Like, this is something that, yeah, if you really wanted to do it, you can do it all the time. But since these types of constraints are so common, let's just create a new way of approaching it. And then all of this sort of very formulaic back-end work will take care of it. So let's look at these indicator constraints. And essentially, these things boil down to if-then statements, where the if part has a single binary decision variable sort of on and off as the if, and then some other constraint as the then. So it boils down to, if this binary variable equals 1, or it can also equal 0, you can also say equals 0. So if this binary variable equals either 0 or 1, some specific number, then enforce this constraint. If it's the other value, then don't worry about it. That's what these indicator functions are doing. So I started the first one in this Z is 1 constraint. I started the first one. So take a couple minutes to fill in the rest of them. So essentially, when Z is 1, what do we want for XPD with, given our prior constraints? And then also when ZPD is 0, what do we want to have happen? And again, this is sort of thinking back to other session and everything like that. So take a minute to figure to write that in, code that in there, and see if we get the similar stuff here. And for those of you asking questions about anything pertaining to like modeling of this stuff, feel free to keep plugging away at any other questions that you may have. All right, let's add in this stuff here. So when z is 1, we want this to happen. We want x to be greater than or equal to c. And when z is 0, we want x to be less than or equal to 0. And again, you could put in x equals 0. Again, since we talked about the non-negativity of x means that you can get away with this sort of more loose definition here. I've just been sort of keeping that consistent, but you can use equalities in this as well, in this right-hand side. So this is what we have for our indicator constraints. So we're done. Let's optimize. Let's look at the solution. And it looks exactly the same. And that's because it is exactly the same. We modeled the same thing twice. And that's fine. So we just sort of show two different ways that we can approach this. This was much faster, a lot less if-then stuff, a lot less all of that sort of transformations of the logic and everything. That's all it's very formulaic, it's very repeatable. So on the back end, we created a function to help with that. So what's great about doing stuff like this is a very intuitive form to look at. So somebody can understand what this constraint is really saying without having to go and say, okay, well, we have these auxiliary variables that do this and this other set of auxiliary variables that do that. And it gets kind of convoluted to understand someone's model and particularly understand someone's code. So having these types of functions that simplify these things really makes the code more readable, makes and makes it just easier to dive in, easier to debug, easier to understand what's going on, easier just all around. So that's why another reason, in addition to all of the big M stuff that I was talking about before, another reason to use these things is just it simplifies the code, and simple code is great. So we have our solution. All right, that was easy, but can it get easier? And the answer to this particular question, is, I see a question that popped up, and I kind of want to hit on that actually. Do indicator constraints use big M under the hood? Again, Eli, correct me if I'm wrong, but the answer is yes, I believe. Is that true?
I think the answer is it depends. Gurobi may try to introduce a big M constraint to model it, or alternatively, it could use SOS constraints, which are handled internally differently by Gurobi.
Okay. So the answer is maybe, but the thank you. But that, to my point, is that it is good to trust to trust that the solver knows what it's doing in these instances. So if it is better to use big M, then that's what will happen under the hood. If it's better to use, and what Eli mentioned was SOS constraints, it's something that we're not talking about in this training, but if we have another one at this level, that definitely will be there. That is another way of doing it as well. So so essentially, excuse me, and that's why I think using these again is another good reason, is there's a lot of smartness that's going on behind the scenes and under the hood. So it is a good idea to sort of just say, hey, here's what I want. What do you think is the best way to go about it? And we have built in the back end ways to identify the proper, the most efficient way of modeling and solving these things under the hood. So very good question. So the last way that we can use is something that's called a semi-continuous decision variable. And this is very specific to this type of constraint that we want, where we want a decision variable to be either 0 or to be within some bound. So it's either off, and then if it's on, it's constrained. And that's what we mean by a semi-continuous variable. So let's remove our other constraints, and we'll just sort of say, okay, I recognize that I can use a variable type of semi-continuous here. So that's all you need to do. And that's the only difference between what I have all here and the very original problem, where I specified the lower bound to be C. So again, this is saying that X must be equal to 0. And the lower bound is C. Let me see here. Whoops. Let me check. Okay. Make sure I'm working on good time here. Okay. Yeah. So far, so good. So the next session is in 25 minutes. Okay. I just got a reminder, making sure that I'm on schedule here. So we can just run that, and here we go. Everything else is the same. Our solution's the same. Yay. And that was even easier. So again, a great way to understand the relationship between big M, a new variable type, and also a new type of constraint called indicator constraint, which again, the indicator constraint is very, very powerful. Okay. Oops, that's why it's not scrolling. Okay. So let's talk about a couple other things here. And if we do run out of time, I think that's fine. I was worried about going too quickly. I did a really good job of padding. So let's say we want to constrain our production facilities. So all throughout this, our decision variables have been the amount to send from one location to another. Now we're going to talk about what happens if we think about turning on or off facilities as a whole. So maybe the facility in Charleston doesn't do anything, or the facility in Baltimore doesn't do anything, or the facility in Cleveland doesn't do anything, and it's just completely off. That may be a very valid thing that you want to look into. If we do that, though, we're going to have to change our model a little bit. One thing that I did was I updated the production just because we need to make this run. But we also need to get rid of that must produce constraint, because if we're going to turn off a facility completely, saying that must produce something is contradictory to that. So we need to remove that constraint. So let's do that. And we're going to set the same objective and run that as well. So everything's good. And let's optimize to establish a baseline. So this is, if we were to say, if we were to essentially get rid of that, that must produce constraint, this is the solution that we would get. So let's add a new decision variable. And this is one that we talked about in the prior session, that models the yes or no decision to open or have or close a particular facility. So let's add that in. But before we do that, let's add the type. So a quick 101 recap. How do you establish a decision variable to be binary? And I'll go through this one quickly. grb.binary, and again, integer similarly. And if you're doing continuous, that is the default. You don't need to necessarily you don't necessarily need to type that in there. So now we have y. We want to make sure that now we want to talk about the link between XPD and YP. Again, this was the on or off decision is done at the production level. So we're going to use a big M approach to do this. So essentially, what did we talk about in the last session? So this was exactly what was posted. Since that was exactly posted, I'm going to do this a little bit quickly and give you maybe a few seconds to think about what that was. Think about, okay, what did we say in the last one? How do I code that up real fast? And what I left out here that I kept in the other ones is the indices and sets that you have to sort of loop through internally to make this happen. So again, a little bit of a one-on-one thing to a quick review. So here is our constraint. Then that the XPD must be less than or equal to the max production times our binary variable, yes or no. And then this is looped across the production and distribution combinations. So again, this was the poll from the last session. If you decide to ship ship widgets out of P, then you have to have this facility on. The other way around isn't necessarily true. It's more than likely going to be true. You're not going to, it's very unlikely that you would open up a facility and then do nothing with it. But you can always concoct an example where that happens. If I had if it cost me negative amounts of money, if I to do this, to open this facility, then yeah, I can just open it up and not do anything. So I can make such an example happen. But I can't make an example the other way around, where we produce something, but this isn't on. So again, it's a little bit of a tricky thing, but that's the logic behind it. So we have our big M, we have everything here. So let's look at a regional restriction. I decided to finally name this company Bridget's Widgets. And the more I say that, the more I'm going to mess it up. But let's say that they have a requirement, the management there says that if the production facility in Charleston is open, then Cleveland cannot be open and Baltimore cannot be open. So let's think about what that means and if then it and go from there. So that means if the Charleston is open, that means Cleveland is closed and Baltimore is closed. And that is what this if then statement is saying here. If Y sub Charleston is 1, meaning it's open, then Y sub Cleveland is 0, meaning it's closed, and same for Baltimore. So given what we've learned about indicator constraints, this seems like a really good approach to do this, because indicator constraints, the left-hand side of this should be a binary variable. That's exactly what we have, part of the if. So what would that look like? Oh, I got ahead of myself a little bit. Oh, that's fine, because we're getting closer on time and I want to make my way through some stuff. So that right-hand side of Y Cleveland and Y Baltimore, saying that both of those need to be equal to 0, how we can sort of have a mini constraint that needs to go on the right-hand side of this indicator is Y Cleveland plus Y Baltimore must be equal to 0, because we want both of them closed. And again, these are binary variables. So if the sum of them is equal to 0, that means both of them must be equal to 0. So then so here's, I'm going to give you a few minutes or a minute or so to code up the whole constraint for this. Again, it's just one constraint, as we can see by we're using add constr, not constrs. So we're adding one single constraint. So take a second to take this statement here, the if Charleston, then Cleveland, Baltimore thing, and plop that in using an indicator function, indicator constraint. And a quick reminder of if you do have questions, they will be seen much faster and replied to much more quickly. If you use the Q&A feature as instead of the chat, we'll try our best to get to all of them anyways, but that's the better way to go about it. So what does this indicator constraint look like? It looks like this. If Charleston is equal to 1, then y Cleveland plus y Baltimore equal to 0. So this is, again, why this type of constraint is really, really awesome, is because it's just very intuitive to see it and read it and understand it. So then I also added this statement here you also have the ability to write, and I talked about this in 101, to write your models out in an LP form. And an LP form is a somewhat, I guess it's human readable. It's a little hard to maybe understand exactly everything that's going on because it is very, very long sometimes. But it is a great way to look at your model and see if you wrote constraints properly and if decision variables are defined properly. It's a great way of going about that. So we won't look at it. I have it there. I suggest that when you run this, take a second. It's always a good idea to write that type of file, and you might be able to identify some obvious errors. So let's optimize. And let's see what our solution is. Our solution, and here's what our optimal solution looks like now. And as you might expect, if we're saying if one particular facility is open, then 2 others must be closed, that's pretty restrictive. So it makes sense that maybe that didn't happen. So we see that the facility, the Charleston facility, we decided to close it because it was just being too restrictive on our system as a whole. So let's remove this, and we got about 15 minutes left. I think we're doing well. All right, may even have a few minutes left for a quick break before we get going into the next session. We'll see. So I hope that was a good way of introducing the indicator function and just sort of why it's just really awesome to use, because it is just easy to read, easy to implement, and I highly recommend it. So let's answer a different question. Now that we have our link between the X production variables, we want to see we may have a question. It's like, okay, I have all this demand, I have this potential supply. What's the smallest number of facilities that I can have open in order to meet my demand? That's a very, very different question than what we were talking about before with minimal costs. But it's an easy one to sort of just code up and see what happens. All we need to do is just change our objective, which you can just continually update your objective by just using set objective. And it's just the sum of our y variables. We want to minimize that. And another thing is I didn't set the sense, which is, again, maximizing or minimizing of this objective, because by default it's minimization. But it's always a good idea to maybe include that. So here's me not having best practices, I guess. I apologize. But let's run this and go through the log, and let's see. The solution count is, we have 1 solution, and our best objective is 4. So meaning that for us to satisfy this demand with this, these production caps and everything, we do need to have 4 facilities open. Let's compare the cost of this to the original cost from the baseline that we set not too long ago. I run that, even though the answer is right there. And there is some difference in cost, obviously. But does this really say anything for certain about the cost of using only 4 facilities? And the answer to that is no, because in this model that we just ran, we didn't say anything about, we didn't prioritize anything about the facilities. We just said, give me the lowest number of facilities, not the best 4 in order to do blank, or something along those lines. So this cost that you may extract from here is kind of not relevant. So this is a little bit of a cautionary tale, I guess, more or less, is what you want to make sure is you want to make sure that given your objective and given your constraints, that the information you extract from that model is actually it's that you're interpreting it correctly. So when we just ask the optimization model to minimize the number of open facilities, again, that has nothing to do with the cost at all. We're not saying anything along those lines. We're going to talk about later, and particularly tomorrow, how can we maybe blend those types of things together. But again, we didn't set anything with the cost. So the value that this chose of 4, there could be other combinations of 4 that will meet demand. It chose 1. So again, maybe there does exist another set of 4 that will have a smaller cost. Maybe there's another 4 that will meet demand but has a higher cost. So again, since we didn't specify much about the cost and how it relates to this problem that we just solved, then you can't interpret anything from that. So, okay, let's add a constraint. So now we just sort of saw that we need at least 4 facilities. Let's or maybe we have exactly 4 facilities. We're going to go with that. Let's say I was changing some stuff on the fly here, but let's not do that. Let's see what happens when we have the number of production facilities be at most 4, and we actually implement that as a constraint. So let's add a constraint to the M2 model that says that the number of facilities open must be at most 4. So I'll give you a few seconds to think about that. This one, again, is a little bit more of a one-on-one type of constraint. And again, it's a single constraint, so make sure you use this add constr and not strs. Okay, so let's add this here. So saying that the facilities must be at most 4. We want to add the constraint that the sum is less than or equal to 4. And we want to minimize, we do want to update our objective to the total cost again, because now we're incorporating this idea that we need 4 and having a now minimizing cost. So we're incorporating cost there. And let's optimize. And we see that we have a cost of 1662. And we can compare this to other solutions. And I do want to move on to like the next part. So I'm going to skip over and move on to one more thing because we're running out of time. I definitely want to hit this up. So through the in the last session, I talked about using maxes and mins and how it could be pretty cool. and how there can be an idea of maybe some fairness or something along those lines that will make you want to maximize the minimum number of widgets shipped. So there could be this scenario that Bridges Widgets wants to transport as much as possible per shipment. One way to interpret that statement is to take whatever the minimum shipment is, which we saw at one point was 2, and we have then bumped up to 30, and so on and so forth. We want to make that smallest value as large as possible. So we can do that by using some general constraints that that Gurobi has that talks about how do we set things to the minimum. And then I'm going to talk about how you don't necessarily need to do that. And I have 2 ways of going about it. I'm going to choose, so you can use what we call like this overloaded form, and then you can use a general constraint form. And I'm going to uncomment this because we can see it a little bit. But we want to say some value R is equal to the minimum of a set of decision variables. So we're going to set R to be equal to the minimum of the of what we ship from any location P to any location D. So we use this constraint that says R is going to be equal to GP dot min underscore. So that is saying, give me the minimum of what I'm going to plop in here and set that equal to R. And that's XPD for P in production, D in distribution. Oops. That. Oops. There we go. I knew I had it right the first time. So we can add that and then set the objective to maximize R. So we're maximizing the min of the decision variables. And here's our solution of 21. And saying that we can do this with a minimum, like if we wanted to maximize the minimum shipment, that's our objective there. And this is going back to using all this newer data. So some of the values that we had in our head from way back when aren't really the same right now. So can we actually do this a little bit more easily? The answer is yes. And it comes from the fact that we are maximizing a minimum. We can just say that R needs to be less than or equal to each XPD. This is what we talked about a little bit in the previous session. So we can just implement that constraint. And the fact that we're maximizing will sort of take care of the other part of it. So we don't actually need to do this equivalent, saying that R needs to be equal to, but in other instances we may. So we run that, we get the same solution, and everything's great. So I think we can end just a few minutes early, give everyone a second to catch their breath, particularly me, and then head on over to the next session. So I think that's it for now, and I'll see you all in a few minutes.